So hello everybody and welcome back to Copenhagen Suborbitals and current affairs, and we've moved outside today, I guess because spring is upon us. I'm standing here with Martin Petersen, and today's focus is on all the complex and wonderful development work going on in the Capsule section. So welcome Martin.
Thank you.
We have at least 3 different small things we need to go over today. All of it is going to be Capsule focused, but before we get to this, what is your role in the Capsule department and Capsule development?
Well, for the past couple of months, or maybe almost a year, I've been sort of a lead, project lead on the Capsule, and also a designer on the Capsule, and now have moved away from the administrative part and more into just design and development. And so that's what I've been working on the Capsule for the last year or so.
Well, let's just do a little recap because and take some of the prime requirements of. We're building a space capsule for a man. That's the obvious part of it, but what is that? What is it we're looking into then when we're looking into the development of the capsule? What is it? Can you give us a sort of an insight into what are all these factors we need to take into account, because it's not simple.
No, obviously there are some restrictions on the Capsule because we need to keep the rocket as small as possible, and so that's why we have decided to go with a capsule that is, or a rocket and a capsule that is about 1 meter in diameter, and we will look into that on the scale model, or the 1-to-1 model actually a little later, and then it has a height restriction as well because we don't want the capsule to be too heavy, and the longer it is, the heavier it also becomes. So that's sort of the restrictions that we're working within.
Because complexity-wise, now that we're talking eventually manned spaceflight, then my personal impression is that the capsule development is at least as big a part as the launcher and the booster rocket development itself, because it's a sort of a self-sustaining system that needs to be able to do more stuff and just as safe as the rest of the rocket.
That's true. It's not as long and as big as the booster section, but it is, I think, equally a complex system. As you say, it has to function autonomously when it re-enters. When we reach approximately the maximum altitude, the booster section and the capsule separates, and then on the way down it's the capsule that has to do everything itself, so with parachutes and all of these things. So it is a contained system that we are designing.
Live support, computers, telemetry, as you mentioned, parachute and backup parachute systems,
cameras, everything.
Yeah. So it's I'm not sure if people actually thought of it, but it's a huge project. Just as huge as the launcher itself. So we're going to look into some more of this, because you just don't do a capsule space capsule in a month or a year. It's a big process. So what are some of these things? How has this capsule development been attacked?
Well, the main focus has been in the beginning to get the overall dimensions in place, and that's why we have something that we're working on now with the 1-to-1 scale and also the smaller scale components. And the second part is to try to see what design is necessary to ensure a safe return and impact into the water eventually when we land. And so there are different design suggestions or design attempts on that. And that's one of the things that we want to test within the next coming weeks to get an idea on what design we are continuing on.
So just before we get into the discussion on all the small interesting pieces we have here, what has so far been the most important part of the descent from space to focus on?
I would say it's probably the impact. The descent down through the atmosphere is one thing. We have payloads and parachutes and whatnot to keep the G loads down and the speed down, but the impact with the water is probably one of the biggest concern right now, because it will land at approximately, I think it's 8 or 9 meters per second under its parachutes, and that will give a pretty high impact if the astronaut is not some sort of suspended, or if the design take into account the impact with the water.
Yeah, I've seen some of the numbers, and it's a rather abrupt shock once the nose or the end bottom of the capsule slams into the water. It's actually some pretty significant forces. It took me a little bit surprised that they actually were that big.
Yeah, so it definitely put some challenges into the design of the seat suspension and the capsule design itself.
Okay, so how's this water impact been handled so far or tackled? What's happening?
We
there?
decided to do a scale test first, a small scale test, because it's easiest to do, and that's why we have made or designed this 1 in 10 scale 3D printed capsule, and so we're going to try to throw this into a swimming pool to see how it performs. We will put in a sensor, a data logger, that will measure the accelerations and other things, and thereby get an idea about how different, for instance, different designs of how that will impact the G loads the astronaut will, or the capsule will sustain. Because one thing is what the capsule experiences, another thing is what the astronaut will experience, and that's something that we will also get into in a few minutes.
Yeah, I guess it makes sense, because if you have a completely flat bottom and you slam that into the water, it's going to be a much bigger shock than if you have a very long pointy one that just slices through the water.
Exactly. Those are some of the things that we need to look into.
Okay, so this little scale model here, if fully equipped with sensors and so on, what's the goal of, yes, evaluating the G sensor loads of what we throw into the water, but is it, what's the real benefit and what's the real value of using that little scale model?
It's, I think it's something to help us with the further development, because once we have evaluated the measurements and the data, we can then see, okay, what is the overall general direction to go in with regards to the design, and after that we can maybe go up in scale to maybe 1 in 3 and throw that out from a tall building or into a pool, or to do some of these free fall and impact tests, because it's much easier and cheaper to do the smaller scales rather than to do a 1-to-1 scale and just test on that directly.
So you had this one in several different pieces, so it's completely reconfigurable, so we can more or less put whatever kind of nose and back end and so forth on it.
Exactly. I mean, it consists basically of 3 components: the end bottom, the cylindrical part, which is where the astronaut is, and then the end part, or the top part, with this, which would be the parachute compartment and nose cone. Assembly
it will
thing.
eventually be covered up by the nose cone.
There will be a nose cone up here somehow, and so this can be taken apart. There's a threaded stud inside, so we can exchange various designs of these and test those at will.
Yes, and also move around a counterweight inside to experiment with the center of mass and stuff like this.
Right, because right now we don't have a precise idea about the center of gravity, so we will have on this threaded stud a metal disc that we can move up and down inside to change the center of gravity and get an idea about, get a sense of how that impacts the descent and the impact on the water.
Also, another thing, you have these notches on the cylindrical part. What's the idea with those?
Yeah, we've seen some calculations that the end of the bottom here does not have a big enough area to actually slow down the capsule down through the atmosphere sufficiently. So we have done some different ideas and concepts on how to increase the surface area, and one of the ideas is to use a sort of a grid fin concept, similar like other professionals are also doing. And so we want to try, not so much for the water impact test, but more from the free fall test from high altitude to see, or higher altitude, to see what this means for stability and drag. And so we have a concept of 3 of these on here to see what does that do. And we have a couple of different design. We both have it with the squared and with the diamond shaped, both to see what the if there's a difference in drag, and also to see what the difference is in 3D print ability is on these two designs. So that's what we're going to test with this as well.
Yeah, because I also remember seeing some numbers from those simulations. I mean, the thing, or the shape of the capsule we have is so markedly different from basically all the other capsules that has been around since the 60s, which are these very cone-shaped with huge frontal area. And I do remember some numbers that we were coming in at speeds way too high because we simply didn't have enough frontal area to do some aero braking.
Yeah, precisely. And so that's what we're going to try to see if this will help in any way, or if this is just a silly idea that we can't use for anything. But it's part of development, and it's to try different concepts.
Okay, so when's the scheduled dumping of this one into swimming pools?
Well, right now we're just waiting for the delivery, basically, of the sensor that we want to mount in there, and then this needs some painting and stuff like that. So hopefully within a couple of weeks we can go and throw it into the swimming pool to see what happens.
And see if we can validate all of that other simulation that's been done.
Precisely, yeah. There are some scale laws and formulas that we are using, and to see if we are in the right track and get the same results that we would expect from using these formulas and calculations.
We'll go more into the to this part about the high altitude descent at some other better occasion. I mean, right now it's actually two distinctively different parts, because right now we're focusing on the very short travel length of hitting the water and making sure that we don't break the astronaut in that process.
Yeah.
And then we'll get to the high altitude stability and air braking and so on later on.
Yeah.
I think we'll just we have a couple of other very interesting things here we wanna take people through. So which one should we go for next?
I think we should go for the big 1-to-1 scale steel capsule that we are working on to get an idea about the actual size of what the capsule will be.
Yeah, I think we've been over this before, but we'll just recap it. I mean, this is known as a boilerplate mockup. It sounds weird, but what's the idea?
It's a very simple steel. It can be done in different ways, but we've made it in steel because it's easy to work with. It's easy to weld on stuff and cut it off again if we want to move things around.
No, not here. That one goes there, and then move that one over there.
Exactly. So this is easy to work with, to get an idea where the astronaut is going to be, the positioning of all the different systems inside, hatch, windows, all these things. So that's why we have made this. But right now it's still just a cylinder. We still need to decide the placement or the positioning of the different hatch and windows and whatnot.
I think it's actually a little bit off topic, but one of the biggest thing that this thing taught me was, first of all, I mean, this is just a little part of the capsule which is actually pressurized, but that's going to be the diameter of Spica, and then it's going to be yay high. Yeah, it's going to be a freaking huge rocket.
It's going to be a big rocket for sure.
I mean, this one over here wouldn't even fit as a side booster. So, all right. But this one apparently does another trick besides looking great.
We're using it for two different things, both to as it is here in vertical position, just to get an astronaut can get a feel of what it's like to sit in a harness eventually once this has been mounted inside. But it can also flip down so to gain easier access for systems and stuff like that. And I can also give an idea about the size of the capsule once it's positioned in vertical. We can see the diameter more clearly.
It's also going to be awesome for giving people some. Once we start doing the interior decoration and stuff like this, I mean, this section here is going to have a little ladder in front of it. Then there's going to be the hatch opening, and then we're actually going to invite people inside. So if people come by or we go to exhibitions or whatnot, then people can actually get a chance to get inside and actually feel how crammed this little space is going to be, this little bubble that's going to try and keep you alive outside the atmosphere.
Yeah, for sure.
But I know it does the flipping stunt, so let's see if we can make it.
Sure. Yeah.
So now we managed to flip it around, and it sounds a little bit reverberating here, but if you take a look inside that, and thinking of all the other equipment that we're gonna cram in there, then it's gonna be a very, very tight, small space.
Exactly, and I mean, this is also help giving an idea about the place or the volume that is for a capsule or for the astronaut and its seat design. One thing is to lie on the back here with your legs up and you feel, oh, there's a lot of place or a lot of room in here. But I mean, the seat is usually consists of a back piece as well and some framework and there's going to be some sort of suspension dampening system as well for the astronaut. And then all of a sudden, this becomes very small, this volume in here.
And we also, I mean, we still have to, I don't think we managed to find a compromise yet where the capsule actually, the G-loads upon splashdown is actually sufficiently low for a astronaut to go through that without any injuries. I mean, it's not possible to reduce the G-load sufficiently during splashdown, so we also need to put the shock absorbers in here. So even though the capsule might take a 15 G smack when it splashes down, the seat suspension will even it out and maybe go down to 3 or 4 Gs, and then the deceleration will have been completed by the time the suspension is compressed.
Exactly. I mean, we don't think it's realistic to do a design where it's the design of the capsule itself that keeps the G loads down. We need to do some sort of suspension of the astronaut. Otherwise, it would be unsafe for the astronaut without it.
And we need to get it down to like 3 or 4 Gs.
Yeah, something like that. I mean, we're looking into what the G loads are on catapult seats or ejection seats on fighter jets and stuff like that, because we know people can survive that relatively unharmed, and that's the G load in the direction that we expect.
So okay, but it's still empty, and I guess it's gonna be for a while because we're a little bit well, we're not stuck, but there's going a lot of thought and care into the seat design, as we've mentioned a few times. We won't really be able to progress much with this before we actually settled on some seat solution.
Not a whole lot, no. I mean, we do get an idea about the seat position in the other model we have over here that we're going to look at in a little bit. But I mean, I think we can sort of start getting an idea about where the hatch could be and where the viewing ports or the windows could be. So we could start cutting that out within a relatively short amount of time. And then it will start looking more. Then we could get the top end cap on as well, and then it will look more like an actual capsule.
All right, but I guess that's pretty easily and smoothly takes us on to the third little thing we have in stock for today, which is this elusive seat design. I think I've seen at least 6 different concepts by now. But what's different this time from all the other stuff we've been doing?
Well, one of the problems with a traditional seat, like a racing seat or some other seats that we have had in some of the other capsules that we have had, is size and weight. And we know we want to keep the weight down because that's this will be heavy even when it will be designed in its correct material and built. It will still be heavy. So we need to keep the weight down as much as possible. And the other thing is room, as we mentioned. The volume in here, the space is very tight. So we need something that is very compact, and that's sort of the direction and the idea that I've had, and that we're going to try to look into to see if it's viable. It might not be, but it's an idea that we can
part
look
of
into.
the process.
Yeah, exactly.
All right. Well, actually, then let's go over and take a look.
Yep.
Okay, so now we're looking at this latest seat concept. You simply have to explain what we're looking at.
Yes. Well, I had the idea to have some sort of harness that you're sitting in instead of having an actual seat, because then you sort of become the seat. And after some discussion back and forth, also with our parachute guy, Mads Stenfeld, then we looked into a paraglider seat, because they are made to be sit in for a very long time when you're flying around in the air on a paraglider. and it's compact. So this was an idea for a concept, and it seems to be. I mean, it wouldn't be exactly like this, but it's in this sort of direction that we're planning on looking into for the coming time, because it can be easily adjusted in different directions. Similar to a parachute harness, you can there are different clasps and stuff where you can adjust lengths of straps to change your position from almost vertical to lying down a little bit and tightening up your knees and stuff like that. So this is what we're attempting to sort of replicate without actually replicating it.
We're going to see how we can. I mean, it's still just a preliminary idea, but it might actually work. We have to come up with some footholds for the cannonball posture, but all of this is just part of the process. But it does look really compact, and I've seen a few guys sitting in it, and it seems reasonably comfortable actually.
Yeah, and we also have this little mock-up or model of the capsule. It has sort of the same diameter and height, almost the same height as the one we were just looking at. And this can be closed down around when a person is sitting in it. And when we did that last week, we actually saw that even this quite compact design still takes up a lot of space. So it would be very difficult to actually try to get a real seat in here. But yeah, this is what we're trying to see what will happen with.
I mean, space-wise, it doesn't seem that there is a good solution. I mean, no matter what we do, space just vanishes whenever we do anything.
Yeah. So this is going to be one of the big challenges for the next months or two.
Right. Well, I think we've been over a couple of very interesting parts of all this development work going on in the Capsule group right now. So thank you much for giving us some insight to this. All right, guys. So I hope you've enjoyed this little insight into the latest part of our magnificent rocket project here at Copenhagen Suborbitals. So we'll be looking forward very much to giving you some insight, some more insight into other parts of the project very soon. So take care until next time.